Hi, I'm Işıl Bozma. Our title is Verifying the Recognized Place Through Localization. This work was part of Esen's master thesis. However, she couldn't come. Okay, I think everybody here will agree that being aware of one's surrounding is an integral robotic capability. This is achieved either through place recognition or localization. A place here is defined by the set of appearances and locations belonging to a spatial unit. The reliability of place recognition is usually obtained through post-experiment assessment using canonical metrics such as recall and precision. However, the two tend to work inversely. Furthermore, for autonomy, the robot needs to measure the goodness of its decision during operation. In this work, we have been concerned with this problem and have thought about how to improve face recognition decision with coupling with localization. In our proposed approach, the robot attempts to recognize a place using the topological spatial cognition model based on previous experience. This is done completely autonomously, and learned appearances are tagged with relative location. It then estimates each moved location in this place, where the estimate of each position is uses all place learned locations. Each learned location affects the estimate with a weight that depends on the appearance similarity and spatial coverage. These weights are then used to construct a confidence measure, which then the robot can use during its operation to evaluate how good of a decision it made. I'll be happy to talk about the details of this work during the poster session. Thank you.
Hello, everyone. My name is Juan Rojas, and I'm here to talk about robot introspection and manipulation domains, where we want to do anomaly learning and also prevention. So as a framework, we have something that is sensing, planning, and acting, but also introspecting. What we want to do is have a graph of a manipulation task. This graph can be either designed by an expert user or learned from experience. Within each part of the graph, we have nodes that have a duality. One, which is motion generation, and one, which is introspection. Motion generation for us can be done with any kind of technique, end-to-end learning, DMPs, motion planning. But as you're carrying out each of these nodes and executing some actions, we also have an introspection model, mainly driven by a direct kind of like hierarchical Dirichlet process, autoregressive HMMs. Basically, we use Bayesian non-parametric approach to try to understand what the robot is doing. So we're learning from experience, but we're interested in doing two things from the introspection point of view. We want to identify nominal behavior and also anomalous behavior. Identify it and characterize it. So down this model, we have two kinds of classifiers for nominal behavior and anomalous behavior. From that, we are able to make decisions about what should the robot do, whether to continue or slightly adapt or have a complete different kind of recovery. So this would insert additional behavior into our graph and be able to learn new conditions over time. So here, if you look at the system, it's not a video, but basically we do a pick and place task or opening and closing a drawer. And on the right side, we have the manipulation graph through which the robot would be moving. Here on the lower left, we have different kinds of metrics. In particular, we have a metric coming from the gradient of the log likelihood of a hidden Markov model or a scoring model that's proved to be very reliable for us. And so then the robot, when he experiences external perturbations, like a hit from a human and human-robot collaboration, the insertion of an external object and an alignment task, things that a low-level controller couldn't handle, then it would then trigger a recovery behavior. And so here at the end, we just have a graph of the performance. The top one is we can always very stably recognize far away from our anomaly threshold what we're doing that is nominal. And on the bottom, the red lines indicate external perturbations. We never have false positives, and we can always identify when those things happen. So this metric has been very stable, robust, fast, accurate for us. If you want to learn more about this, come see me later. Thank you.
Hi, so my name is David Rosen, and this is joint work done with Luke Carlone from MIT, and I'm going to be speaking a little bit about computational enhancements for certifiably correct SLAM. So my background is actually in perception. Most of my research is focused on the SLAM problem so far, so just in case anyone here is not familiar with how that problem looks, or more specifically the problem of post-graph SLAM, the basic idea is that you're given a set of unknown robot positions. So picture a robot driving through some initially unknown environment, it's moving around along some trajectory. And via things like laser scan matching or stereo vision or optical flow or things of that sort, you can produce some noisy relative measurements that describe how the robot has moved between each of these positions that it progresses through as it moves through the supply. And so through things like localization and place recognition technologies, like we just heard about a moment ago, you can do what are called loop closures, where you generate these links for poses that are very far back in time. And so the result of this basically is that you've got this collection of unknown poses, and you have some notion of measurement. You have some collection of noisy measurements between them. And what you want is you want to figure out the positions of the robot as it explored this environment that are most consistent with the available interposed measurements that you've got. So typically this is solved through maximum likelihood estimation. If you just write down what the form of this problem is, it turns out to be the specific form of this function is not super important. What matters basically is that it's a very high-dimensional optimization problem because each of the poses that the robot went through introduces a new variable. And it's non-convex because you're performing variable estimation over positions and orientations. It's the orientation part that makes this problem non-convex. So you have a high-dimensional, non-convex optimization problem. And so that turns out to be hard because essentially what that means is if you consider the cost surface for the function that you're trying to optimize, it's got lots and lots and lots of local memory. And so all of your data that is coming into your algorithm can be clean, but nevertheless, it's not uncommon for your mapping or pose estimation algorithms to produce really bad estimates like this. And so if you're thinking about using, this is actually a parking garage example, so if you're considering using current state-of-the-art techniques for mapping and localization in the context of autonomous driving or things of that sort, I would argue that if your system is outputting solutions like this, you're going to have a bad time. So in some recent work, what my collaborators and I have been able to show is that we've developed an optimization technique that is actually capable of directly searching for global optima for these problems, number one. And number two, actually generating computational certificates of correctness, that is, computational proofs that the solution that you have recovered is in fact the globally optimal one. So we do this via semi-definite programming to just do the search for solutions and a minimum eigenvalue computation to generate these computational proofs of correctness. But these can be expensive. So what we've done in this in the paper that's in this workshop is we've basically shown how we can accelerate the optimization and minimum eigenvalue computations that are needed to implement this algorithm using a bunch of cool tricks from numerical optimization, and we've released some C++ code that you can check out. The only things I want to mention about this are these are very general kinds of techniques, so they're not tightly adjusted to this problem. So if you're interested in making your inference or optimization techniques blazing fast, you should come check out the poster, and you can get our code online. Thanks.
Thank you very much.
Okay. Hi, I'm Robert DeBortoli, and along with my collaborators at Oregon State University, we're looking at assessing the quality of sonar images. So imagine you have some underwater object that you're trying to inspect. Here it's an X-shaped object, and you have some underwater vehicle that you can use to go down and inspect it. So at the beginning, you collect some good sonar imagery of this object. The X is well defined in image space. But as you go on, the object starts to smear in image space. You can get reflections off of the seafloor, so you get environmental noise corrupting a lot of the image. And then after a while, you get good imagery back again. And so what you quickly realize is that a lot of sonar imagery is very noisy. And this is a problem, because if you want to have a higher level of analysis on this imagery, such as perceptual algorithms or human operators, look at this data, you want them to spend a lot of time on the good imagery and not spend a lot of time on the bad imagery. And so in this work, our objective is to use introspection to identify informative sonar images. And we define informative as containing enough useful information to clearly identify the object. We do this using Atrus convolution. So one thing to note about sonar images is that because of the insonification process, oftentimes the object appears very smeared in image space versus a camera imagery. Also, noise can corrupt the image so much that there's actually more noise in the image than there is the object. And so in trying to distinguish between those two sorts of things, it helps to have a greater context in analyzing these images. So Atrus convolution uses these dilated filters, which you can see on the right, which give us that greater context with which to characterize these different things. Finally, as a little teaser for our poster, being able to identify informative images enables things like real-time 3D underwater reconstruction. So due to the lack of a reliable feature extractor for sonar images, oftentimes a human has to label these images, and that creates a large disparity between actually collecting the information and doing the reconstruction. And so what we develop is a framework to basically identify informative images and then propose them to a human operator who can then annotate the features with which we can do the reconstructions. For more information, come visit me at my poster. Thanks.
Thank you very much.
Okay, so I'm going to keep this quick because I've already said enough here. So the poster presenting sort of builds on from the stuff that I talked about earlier. It's work I did with my student, Isaac Murphy. And we expanded to also generating some semantics, some ways of talking about, okay, we've got all these explanations, how do we figure out what types of failures we've come across, and how do we define these, again, in a way that is useful to talk about the types of machine learning techniques that we can use to troubleshoot different failures that are interesting to the end user. And then in the paper, we also go into sort of analyzing how a few representatives of machine learning techniques can or can't easily provide us with that information. And then if you also want to talk more about the example that I showed during the talk, I will also go through that in the poster as well. So, that's it.
Thank you very much.